So the area under the curve can commonly be used with much of the streamkeeper data that's collected. Streamkeepers often perform multiple stream surveys during the spawning period, which provides some helpful count data. Generally, when designing a program, it's helpful to start with the Module 1 activities, and that's to do a survey of the entire stream length that's accessible to salmon to map out the habitats. And often, over a few years of conducting these surveys over the complete area, we'll be able to identify the stream segments which are regularly used for spawning, and then these can serve as index areas for doing our counts. Then the next phase is to perform successive surveys on those same segments, and then to conduct the surveys at fairly regular intervals, for example, once per week or maybe every 7 to 10 days, as well as to record the counts in a consistent manner. For example, to record spawners and carcasses, as well to make the recordings consistent by the stream segments using the stream inspection logs. So the area under the curve method really requires three key pieces of information. The first is these multiple spawner surveys, and typically we prefer to do 4 or more surveys during the spawning period. It also requires an estimate of the survey life, which is defined as the number of days that mature Pacific salmon were alive in the survey area. And we should also use an estimate that has been recommended by the DFO biologists, as they're the experts on the species and the conditions in the stream. We also require some knowledge of what the counting efficiency is. And this unfortunately it's typically fairly difficult and expensive to estimate. So most often what we do is use an estimate of survey life that has been adjusted for an average counting efficiency for specific stream segments and species conditions. So the survey lives are sensitive to specific conditions. They vary by many different types of parameters. They vary across species, they can vary from year to year, they can vary within a year just based on the arrival timing of fish. So early time fish may have a longer survey life than late time fish. It can also vary between the sexes, so males can have a longer survey life than females, or vice versa. It depends upon the species and the river. It also depends upon what life stages of the salmon is counted in the stream surveys. For example, if one is counting spawning fish versus counting live fish or just fish that are in shallow water. And it can also vary with the type of the river. So things like the size of the river or which region we're in, or the clarity of the stream and the channel type and the location within the river. So sometimes fish that spawn in the lower part of the river may have a different survey life than fish spawning in the upper part. It can also vary with the abundance of salmon. So when there's more fish present, they may have a shorter survey life, and also it can vary with the abundance of other species. So sometimes if there's lots of competition from chum salmon, coho may have a shorter residence time. And we see similar types of patterns with Chinook and sockeye interactions in some systems. So because there's all this complexity with survey life, we really recommend working with the DFO area biologist to use the best survey life estimate for the specific conditions of the stream which the stream keepers are working on. So survey life, as I mentioned, it's defined as the number of days that mature Pacific salmon were alive in a survey area, and it can range considerably within and between species. So here's some examples. With coho salmon, an average survey life that these authors reported was about 11 days, and it can range between about 3 and 15 days. For chum salmon, the average was about 12, with a range of about 4 to 21 days. Pink salmon, an average of 17, ranging between about 5 and 40 days. Chinook salmon, an average of 12, with a range between 3 and 20 days. And sockeye salmon, an average of about 13, with a range between 7 and about 26 days. So it can be highly variable, and even within a species it can be quite variable. So these are all complexities to consider. And here's an example for some Chinook salmon. These survey life estimates are defined as the number of days that mature Chinook salmon were available for counting on the spawning grounds, and these data are all from Fraser River tributaries. And we see that with Chinook in the lower Shuswap, their average survey life is about 5.4 days with a range of about 4.3 to 6.5. The Nechako, an estimate for females only of about 10.8 days on average with a range of 8 to 13 days. And the Nicola with an average of just about 6 and a range between 5.6 and 6.4 days. So within a species, there can be quite a bit of variation, and even within rivers that are within the same region. Okay, so with the area under the curve method, the stream keepers will go out and they'll count salmon within their segment, and then they'll record those counts, and they may go out a week later and they'll survey the same section of stream again and then make another count. And then typically there'll be more fish counted as we get closer to the peak of the spawning period, and then as that passes, we'll typically count less fish on each successive weekly count. We take those counts and then we make a graph of those count data. So here we have some data from the Nicola River for Chinook salmon, and on the first date, September 1st, we estimate there were 0 fish spawning at that time. We then went 4 days later on the 5th of September, and we counted 499 spawning Chinook salmon. And then we went out another 4 days later on the 9th of September, and we counted 2,428 spawning salmon. And we plot these data by the number of days throughout the spawning period. And with this example, when we estimate the area under the curve, we start by looking at the individual trapezoids, these little tiny blocks of time. So here with our counts on the 5th of September was the 499. We add to the count on the 9th of September, the 2428. We divide by 2 and then multiply by the number of days between the surveys, in this case 4, and then we'll estimate the total number of spawning days within that little trapezoid. And we'll repeat this for the spaces between all of our surveys, and then we add up all the area under those trapezoids, and that'll give us an estimate of the total number of fish days. So with this example, we estimated there was a total of 45,263 spawner days. And we'll divide that by our estimate of survey life, which was 5.57 days, yielding an estimate of spawners of 8,130. Often we'll perform studies on a river over multiple years. So here's an example of some data from Nicola River Chinook salmon, where we repeated these type 2 survey methods, where we did mark recapture studies paired with area under the curve, multiple surveys, and we did this across several years. And we wanted to assess the average survey life over a period of years and try and see how much it varied in this system. And we found the average was about 5.9 days. And then we wanted to decide if the average met our science criteria, and if it did, then we would be comfortable with using an average if it had low amounts of error. But if there is a high amount of error, then we may be required to do an annual estimate. We also wanted to examine how accurate it may be to borrow information from one river and apply it to another. So we've expanded this study to other locations within the Pacific region. We're doing some studies up in the North Coast and some in the Central Coast and South Coast, as well as throughout the Fraser. And with this example on the Nicola River, we really wanted to examine how the peak and the shape of the curve may vary through time. So we see that if one looks across these different years between 1996 and 1999, we see that the peak for 1996 and 97 and 99, they're fairly close. 97's a little later, but in 1998 it was considerably later, and we had a very warm year that year with low water flows and high water temperatures, and it seemed like the fish delayed quite a bit before they began their spawning periods. So here we also see how the survey life values can vary between the years. We see a range between 5.57 was the shortest period of time in 1999 up to a maximum of 6.37 years in 1998. And we've continued this study up up to 2005 on the Nicola River, so we have some more information there. Why would we encourage the stream keepers to consult the DFO area biologists for the survey life knowledge? One is the biologists, they have specific knowledge about the species behavior in their area and the conditions of the local rivers. They're also linked in with regional programs which are designed to improve the accuracy of our spawner abundance estimates. And they're informed of new estimation techniques that may better include the uncertainty and the different processes that are used to develop the estimates. And they're also the local experts on the estimation of salmon spawner abundance. So uncertainty in the area under the curve method, well, we all know that the world is complex, but we're basically stuck in a situation where we'll try to do the best that we can with what we have. And survey life varies with many conditions that we described. It also is influenced by the observer counting accuracy, which can vary with the conditions and between years, as well as the underlying models can vary that describe the salmon behavior can vary. And even within a species, they can vary between different regions. So in this illustration, we have Chinook salmon from the Nechako River, and we have coho salmon from the Tranquil Creek, which is over in the west coast of Vancouver Island. And for the Chinook salmon in the Nechako River, we fit what we call a normal shaped curve to describe the dynamics of the spawners. And we see that there's some variability around this curve. The curve is the best fit, but the red circles are the actual counts, what was actually counted. One can think that the counts may vary in their accuracy just due to things like some days you have sunny weather conditions and you may have a lot of reflection. Other days there could be clouds which contribute to low contrast in the light and trying to see fish compared to the bottom of the river. And it has a very stable hydrograph in the Nechako. The flows are regulated in that. So we get a nice, what we would call a fairly well described normal shaped curve. Now for the coho salmon over on the west coast, we have completely different circumstances with different biology of the animals. Often the rivers on the west side of the island will be very low until the fall rains arrive, and generally the coho salmon will stay out in the estuary or in the ocean until those rains arrive. So here we see that we have a different type of model fitting our count data, and we have very low counts through late September until the rains come in early October, and then we have a big rush of fish entering the system, and most of those fish will kind of stay there and then do their spawning and then slowly die off. But during the spawning period there can be more rain events, more fish entering the system, and we'll have new spawners arriving and replacing. So it's a little bit more complicated than the example that we went through for Chinook. But this is just an example to indicate how the dynamics and the behavior can interact with each other and produce different types of estimates. So biologists, they'll often use a variety of complex analytical methods to try and incorporate some of the uncertainty in the estimates. And we aim to report our escapement numbers with these measures of uncertainty. So sometimes we'll report confidence intervals or precision, or we'll indicate the bias or the error levels in our estimates. It's something that we aim for. We don't always do, but we should be doing, and we encourage others to do that as well. For the application of the area and the curve methods, we've described some simple approaches with the trapezoids, and we've also described some complex approaches. Generally, when comparing them, simple approaches, they often incorporate minimal biological realism. So we talked about a situation where we had one value for survey life, and we tried to combine some of our estimates of observer efficiency in there, just average within a year. And then we also talked about averaging across years, as well as we talked about trying to borrow information from one system and apply it to another. So really we're breaking things down into kind of a blunt instrument that will still provide good quality information that we can use to make scientific inferences about the abundance of salmon. These single parameters often represent a combination of multiple variables, but these systems, they can perform quite well when the variability and the spawner abundance varies more among years than it does due to these other smaller sources of variability, the counting efficiency and everything. So really the main driver in the abundance estimate is the number of fish days, how many fish are out there. For the complex approaches, they'll often try to incorporate more biological realism, and there's fancy ways of trying to model the uncertainty for each of these individual variables. And the methods can perform quite well when studies have been conducted to measure the variability from all these different contributing circumstances. But they can also perform quite poorly when one makes assumptions about the sources of the variability, and it can lead into false confidence in the estimates. And for the simple approaches, they can also perform quite poorly if they're applied naively. So if one just takes a value of residence time from a published report or something like that and just applies it blindly to a system, or without considering some of the details, the species details, or what is actually being counted. And so those are just some of the benefits and pros and cons of each of them.